Dear students, welcome to lecture 18. This is part 2 of free radicals. So today we will continue our study of the reactions of free radical, and we will pay some attention to halogenation of alkanes. In this reaction we have studied last semester, in which we have seen that methane, when reacts with chlorine, it gives a mixture of chlorinated methanes like chloroform, dichloromethane and carbon tetrachloride. This reaction is also possible in the presence of heat or light, and it involves radicals. First step is radical initiation, in which the chlorine gas is in the presence of light or heat generates chlorine radicals. These chlorine radicals then are involved in the chain propagation steps, which involve the proton abstraction from the methane to give HCl and methyl radical. This methyl radical then reacts with the chlorine molecule to give methyl chloride, and further we get a chlorine molecule. This chlorine atom can further react with either methane molecule or with methyl chloride and generate the series of mixtures that we have seen here. But these chains can propagate as long as chloride free radicals are present in the reaction mixture and methane is available. But after some time you will find that termination reactions start to dominate, because two chlorine molecules come close to each other to give chlorine Cl2. Similarly, methyl and chlorine radical will react with each other to form the methyl chloride, or two methyl radicals may bond with each other to give methane. As the reaction proceeds forward, the concentration of the methane drops down, and therefore less of it is available for the reaction, and more of these radical termination reactions will take place. So can you explain this question? Pause this video now and read this and try to answer. Now let us try to pay some attention towards the stereochemistry of the free radical reactions. Whenever radicals are involved in any compound containing chiral centers, total racemization or partial retention of the configuration at the chiral center will take place. Let us try to understand why this happens. This can be understood by considering the structure of the free radical intermediates that are formed. So for example, in this reaction, chlorination reaction of 1-chloro-2-methyl butane, chlorine radical first abstracts this proton, which generates a sp2 hybridized carbon radical. This carbon radical is planar because it is sp2 hybridized, and the radical character is on both sides of the plane, and therefore the incoming chlorine atom could either come from the top resulting into this compound, but it can equally come from the bottom resulting into that isomer. Therefore a racemic mixture is formed and attack from both sides is equally likely, and therefore we get a racemization. But this is not true for all reactions involving radicals. For example, this photo isomerization of this azo compound, that is 2-phenyl azo 2-phenyl butane. If we heat this compound, this carbon nitrogen bond, because of the steric hindrance, breaks and generates two radicals. These radical, they are not separated like this radical, but they stay quite close to each other, and while they are close to each other, this bond may rotate. If it does not rotate, the radicals will react with each other to form the same compound that one started with. But if these radical pair survives for long, the carbon-carbon single bond might rotate, and because of this rotation it will generate the isomer at this isomeric configuration at this center. Then when the radicals paired with each other, they will form the S compound instead of the R compound, and that is why we find that when you heat this compound, some molecules react in this fashion, but some molecules react in this fashion, thus giving partial retention. Now next reaction that we want to study is the fragmentation of free radicals. As we know, free radicals initially formed, they are very reactive, so they will react with some other compounds to generate either free radicals or neutral compounds. But if they don't react with anything soon enough, then they will fragment into neutral compounds and other free radicals. And this they do because they form a combination of more stable radicals and molecules than the original ones. And this can be exemplified by this example. Benzoyl peroxide initially formed this radical, but if this radical doesn't get access to other molecules to react with, then it slowly will fragment, and it will fragment into a phenyl radical and carbon dioxide. Because carbon dioxide is a gas and it can fly away, the entropy of the system will be higher, and therefore this fragmentation is favored in many cases. Similarly, this optically active compound, when it is treated with acetone in presence of light, the acetone radical will be generated, which will transfer the radical character to this molecule by abstracting this proton, and then the radical character will be generated at the carbonyl center. This will lose molecule of carbon monoxide and give us the alkyl radical, because that is more stable than this radical, and then it may further react back with another molecule of the aldehyde to give the racemic compound. So this fragmentation and rejoining of the radicals can be seen and understood from these examples. Now next set of reactions we want to study is the substitution reactions of free radicals. Free radicals are known to abstract hydrogen atoms from CH groups, and this leads to substitution at the carbon atom. For example, if we treat the 1-phenylpropene with a brominating agent like N-bromosuccinamide, it will brominate at the terminal carbon atom and give us 3-bromo-1-phenylpropane, also known as cinnamyl bromide. Now let us try to understand how this reaction happens and why this compound N-bromosuccinamide is called brominating agent. In presence of HBr, it will abstract the proton from HBr and form the bromine molecule. This bromine molecule will react with the radical generated through peroxides, that is dibenzoyl peroxide will react with this compound, abstract this proton, generate this radical. This radical will then react with the bromine generated in this reaction, and it will give us the brominated compound and a free bromine atom. This bromine atom will further react with the compound to generate free radical, and the process will keep on going on. Next set of free radical reactions that we want to understand is addition reaction of free radical. This we have studied in the last lecture, and anti-Markovnikov's addition is an example of that. Another reaction is the oxidation of free radicals, in which alkanes, when they are treated with peroxides, they form radical initially, but this radical, if it is comes in close contact with oxygen molecule will add, because we know it is a diradical. So one electron, unpaired electron, will pair with this electron and the other will remain unpaired. This molecule can then further react with butane to give us the butyl radical. In effect, this butane has got oxidized and the reaction will keep on continuing. And as much as the oxygen is available, the alkane will get oxidized even in the presence of small amount of peroxide. Similarly, this reaction can be exemplified that the peroxide is breaking to give us the hydroxyl and the alkoxyl radical. This is then losing a hydrogen from here to give us the aldehyde and the alkyl radical. Similarly, we can see that aldehydes in the presence of peroxide will lead to acyl radicals. These in the presence of oxygen give us the peroxy acid radicals. These in the presence of the aldehyde, which is coming from the same reaction mixture, will give us the aldehyde radical, which will continue the cycle, whereas the peroxy acid component fragments to give us two molecules of acids. So aldehydes can be converted into acids in the presence of peroxide and oxygen in this reaction. Now another set of interesting reactions that free radicals undergo are the reduction reactions. Carbonyl compounds generally get reduced in the presence of ethanolic solutions and alkali via free radicals. So this is exemplified by this reaction. 2-butanone, when it is treated with sodium metal, first electron transfer from sodium to the carbonyl compound takes place. This bonding pair goes to oxygen, gets a negative charge here, and the extra electron coming from the sodium is found as a radical here. This radical then reacts with the proton to form this radical, which from sodium then a second series of electron transfer reaction takes place to give that carbon anion, and which then reacts with the solvent to give us 2-butanol. So in effect, butanone has been reduced to 2-butanol via free radicals. Similarly, we can see that in the presence of sodium ammonia, NaNH3, this sodium will give electrons to the ring and this double bond will get reduced. Similarly, acetone can be converted into pinacol in the presence of metal and reducing agent. Our next lecture will be on carbon anions. See you then. Thank you.